Okay. Buongiorno.
Welcome to the fourth day of the lecture. The first speaker is Denis Bernard, and we continue on the for MLP. Please, Denis.
Okay. So we spent the 4 last hours discussing this slide. So at the beginning, I promised that we will use excuse of looking at quantum stochastic processes to discuss classical one on macroscopic fluctuation theory. That's what I did. And the second part for today, I will try to describe a few aspects, basic fact about open quantum system, quantum channel, and this kind of thing. So, which is a step towards discussing on using quantum stochastic processes. So I recall that one of the motivation of discussing these quantum stochastic processes is try to understand fluctuation of quantum effect in many body system beyond the mean typical behavior. So that's what we did for ours. So I think on this slide, I will only spend 30 seconds. So again, we want to describe fluctuation of coherent processes, entanglement, monitoring. So I will explain a bit how we do it in a mesoscopic system. And the second part of the slide is just to say that we can measure search of fluctuation, if in principle at least. So one simple example of quantum stochastic processes in a many body context is the one which we are called quantum SEP. So I told you what was SEP. SEP was a classical model of particle moving on a lattice in 1D on a line. And this was used as a model to understand transport and fluctuation of quantity related to transport in a diffusive system. Quantum SEP is more or less an analog model. Particles are jumping on a line, but they jump keeping their quantumness, coherences, and the jump is a random variable. So, so I will first start by discussing quantum stochastic. I believe that today I will not go beyond this slide actually, but again. So here you see in DH, so we have operators which act on some Hilbert space, CDAC, and there is numbers which are denote DW and DW bar, which are Brownian processes. So, be a take example, QSEP. So that's a many body context. So we have, so there is some Hilbert space which describes the system. So in QSEP, this is a fog space over, so if there is n site over C to the n, which is something of dimension 2 to the n, with n the number of sites. And the system is described by either a state or a density matrix. So there is a state, so depending on the context, state psi or density matrix. Oh. And if we assume for a while that there is no contact with reservoir, then the Then the evolution of the density matrix of the states will be unitary because it's a closed system. But the but is important. But random. So which means that rho will evolve to rho of t at time t. So if this is rho at t equals 0 is some rho with some ut rho ut dag. And these one are so they are random. Which means that in a way you can think that ut depend on omega. On omega in math, where it's just a way to code that there is some event, some realization of the disorder. No, just a name. Okay. Omega is an event. That is a realization of the random. So it takes value in some probability space with some measure. Blah, blah. So that's general. So the random can be, if all the random degrees of freedom parameters will be frozen. This is the kind of system you look at when you look, for example, at the problem of localization. So you have quench impurities, and these are random. When we think about stochastic, this means that these random parameters are updated in a regular way in time. So every small time interval, you update the random parameter, like in the Langevin equation, stochastic equation. So it's random, but stochastic. Again, stochastic means that the randomness is not frozen for good. It just updated every times, every delta t. On the rules, so again, in that kind of model, dw, dwt, I will do dw bar, so they are complex numbers, they are random objects, I will tell you what they are, but we have already seen them. And when we say we have dht, it means that this is dht, we call it the Hamiltonian increment, is a Hamiltonian, is a operator, the Hamiltonian, which tell you what is the evolution during the time interval dt. Okay, so which means that during time dt, from t to t plus dt, so the evolution to go from time t to t plus dt is a unitary evolution, dht. And again, this dht depends on omega, and here omega in SEP will be just the realization of the Brownian motion, dw and dw bar. Which is the same thing as saying that u of t plus dt times u of t complex conjugate is exponential of I dht. So that's one way to describe quantum stochastic processes in general. So here I am talking about quantum set. So I say that the system is, if there is no contact avec reservoir, the evolution is unitary, which means that the system is closed, but actually it's closed if we put the noise in the same package of the system. So when I say that for each realization, so maybe a remark, so evolution is unitary. If no reservoir, no external reservoir, because for each realization of the noise. This implies that we review the system. So there is a system, and there is a noise, degrees of freedom. So there is a noise. So as I said last time, noise is everything you don't know or you don't want to care about. So there is a noise somewhere. That's the noise. And this is all this package, which is a closed system. So you can imagine that the noise is everywhere along the chain, for example. And what we have in mind is that actually the noise comes, as I said, from the low scale degrees of freedom. So let me go back to the first slide. Oh, no, yeah. So I told you that this kind of model we look at, which are some lattice model, quantum one with some transport property. So if you forget about the two reservoirs, we've used them as a way to mimic mesoscopic system. And mesoscopic system is when you look at a system above some scale, mean free path. So below, there is some degrees of freedom associated to the shorter scale, so below below the mean free path in the case of mesoscopic system. And those degrees of freedom, that's what we call noise. And then you may discuss whether this noise, so these degrees of freedom will keep their quantumness or not. That depends whether the system, this depends whether there is enough time scale separation, blah, blah, blah. So you can extend what I'm going to say with quantum noise, but here I model this degrees of freedom by noise. So if we want to add reservoir, then there will be some extra contact beyond the noise, which are modeled here by the.
Usually it happens in the quantum systems when you have some disorder, you end up with localization with noise, which is a kind of disorder because the hopping are not homogeneous, etc. And you also end up with localization or.
So yeah, the kind of disorder you look at when you look at localization problem, these are quench impurities. That's what I was saying. So the disorder is frozen for good during all the evolution. Here, the disorder is updated every instant. And there is no localization because there is transport. That's what we will look at. So I will not discuss, or I will tell you because I need to. So if there is contact with the reservoir, then what I am saying, the system plus the noise is not anymore closed, it's open. So you have to know how to describe open system. That's what I will do next. So just for the SEP, but you don't care, because we will not do much computation on SEP actually. So what I call DW are complex Brownian motion. So it means it's a sum of two complex Brownian motion with an I, where DB1, B1 and B2 are complex Brownian motion. Okay. Independent one, so there is one along the real axis, one along the imaginary axis. There is a pair of such complex real Brownian motions, so a pair of conjugated complex Brownian motion per edge, if you look at the formula. And these one are, so if I compute dw bar, so that's anytime t, so t, and that's for any edge. Maybe I put a 1 over square root of 2. So dB1 square is dt. They are independent, so then dB1 and dB2 is 0, and dB2 square is dt, so that's dt. So again, it means that, as I said last time, dB is of order dt, so here dW modulus is of order dt. Because the phase, so you can take, that's the definition first. And because we want a correlation between moving to the left or moving to the right. So if they were real, there will be also correlation between the operator which move. We want only some correlation between the move on the left and the right in order to have a diffusive transport. See, if they were real, this will induce an extra term in the movement which will be linked to the, well, it will not be a purely diffusive system. But also, actually, this model comes from an, no, I will not make this. But that's a choice, yeah. Yeah, that's a good argument, exactly. We want, I should have said that. All right, you should give the lecture. So we are talking about transport. So when you have transport, you have, you need a local conservation law, the things you transport. And local conservation law is associated to a symmetry. Here we will have a symmetry, which is a U1 symmetry. But the symmetry will be valid only in law, not realization by realization. So it's why we want to be complex. So maybe I can, I was not thinking about that. So the argument is U1 symmetry. So we usually when you have fermion, you can introduce the U1 associated to the fermion number, the number of fermions, okay? So, so that will be a fermion number. And you have one U1 per sides, and this U1 transform Cj into some phase, and Cj dag into opposite phase. Okay? Dag. That's, at least it defines a U1 on each side. And this U1 symmetry preserves the number of fermions, for example, which is Cj dag. Okay? And that's the generator of the phase. So, and that will be my conserved current, and there will be associated a noisy version of the conservation law for that, but in law. Because if I transform Cj plus, that will be transformed if the phases are not the same as I, theta g plus minus 1, theta j, Cj plus, tag, Cj. Okay? So it doesn't live invariant the Hamiltonian. Ah. But I can absorb this phase in the redefinition of the amplitude. So now I go from Wg, T, T to a new one, which will be theta T J okay? So this means that once I have implemented the U1 symmetry on the Hamiltonian, I got exactly the same Hamiltonian, but instead of W, I will have W tilde. Okay? You agree with that? Now W tilde, so it's complex. I can do that because it's complex. But now the law of W tilde is the same as the one of W. Because I say that that's determined completely the law. I have dWt, dWt is 0, is d bar. There is no correlation between the dW bar, so I have only this correlation here. And that's also satisfied by dW. So in law, it's exactly the same processes. So I have this conservation law in law. But the law is not the same in the two cases. So that's why we take W. Yeah. So I will answer here. So yesterday I told you the way of the Brownian motion was derivative is the whiteness. So we have E. Yesterday I told you that E dw t d no bs. That was mean of t minus s. And then I told you that this is the same thing as saying that bt minus bs square is t minus s. Okay? That's what I told you last time. So that's the same thing as E dbt square is dt. Okay? Which, because, which is true everywhere. And okay, then I don't try. So it's a bit an abuse of notation. I will, but which has a meaning that I will write it as dbt square is equal to dt. Okay? Forget about just to code for the variance. Okay?
Why dt, not just t?
Because beta. What I said yesterday is that this by definition is just the increment of the Brownian motion between time t plus dt minus bt. So here I take, so that's when you look at an increment between two times, it's just the length of this time interval. So now it's dt. Okay. So dB is of order square root of t. That's what we say. And my definition of the Brownian motion is that now I have an index, 1 or 2. So let me call it k, or A. A is 1 or 2. So I can take A, B, and then I put a delta AB, okay? Which means that the Brownian motion along the real axis and imaginary axis, I choose them to be independent. That's my definition. And if I do that, I have what I said just before. Yeah, for each edge.
And we are not correlated in...
No, edge per edge, they are not correlated. That's the definition.
No, I mean not edge and edge, I mean correlation between d omega gt and d omega kt.
Yeah, they are 0. By definition. But, okay, just to say that, so I don't want to spend too much time on the model, but I can. But so that at least you see that it's a way to define. There is some randomness, there is some evolution, and I told you that the Brownian motions, the increments are independent. So every delta t, I have a new variable which is independent from the previous one, and the evolution during time 0 on dt has some randomness. Evolution from t plus dt to 2dt has another set of randomness, which is independent of the previous one, and so on. Okay? Let's define stochastic evolution. And then maybe there is 2 ways to analyze that, and I will describe that, and then I will go to, this will lead me to open system. Oh, maybe before. So another remark. So if evolution is stochastic, then rho t becomes a random variable. So it depends on omega, on the realization, because every time I have a different realization, I have a different evolution. So it depends, okay? So this means that I can compute different, I can look at the moments. So for example, you may look at moments of the states. Rho. If you want the distribution at its distribution. So the first moment will be the mean, which I will call rho bar, which will be E of rho T of omega. But I can look at higher moments. I can look at the second moment, which I don't know how to call it, but that will be E of rho T omega, rho T omega, with various indices here. So that could be, it's a matrix. So a way to code it is just to say tensor product. Okay. And so on, etc. Alternatively, it means that I have two notions of mean in such a quantum system. I have the quantum mean, the mean on the, using the quantum states, and the mean using the mean over the realization of the dynamics. So this implies that for any operators on H, so let's call them O1, O2, etc. You may compute, so there is a notion of, there is a quantum expectation, which will be trace over rho times O, O1, trace, so that I can say that this is O1 times T, if this is I times T. And then there is the same thing with O2, etc. And these are random variable because they depend on omega, on the randomness. So these depend on omega. So they are random. So there is a statistical expectation, which is, for example, I can look at expectation of O1 T of omega, which will be expectation of the trace of rho T of O1. But I can look also at the fluctuation of O1, O2, etc. So the easy answer is say, first look at finite dimensional system, n finite, very super large if you want, but finite, then there is no problem. If n is infinite, you have to give the meaning in which sense you take the limit n goes to infinity before answering the question, because then the question is difficult to answer. Yeah, so to take the average, the way to trace out. But if the trace is finite dimensional, this is a finite sum. So it commutes with Fubini, you use whatever theorem you want with a statistical measure. So as soon as you are on a finite dimensional space, no problem. If you are not, it's exactly like in Fubini theorem. You want to exchange two integrals. It's the same thing. So you have to be a bit careful on which space you are and so on. So I think it's not so easy to just answer globally the question. Okay, so then I will describe two ways to discuss the dynamics. So how to deal with such dynamic? So there is the first one, let's say, continuous in time. It's a big word. So as I told you, so we have some DWH. which depend on omega, which is a realization of disorder, of random. And so d plus dt h is equal to times t dag dht. Or if you want, rho, or equivalently, I just say rho of t plus dt is exponential of e dht, rho of t minus e dht. For each realization, okay? That's just a stochastic equation, exactly the same as we had in the classical setting, except that the variable, which we often call x, are now the state of the system. So it's just a classical stochastic equation, but in the space of quantum states. So we just study it as a many variable stochastic equation. So if so that's it's a classical SGE in the space of quantum states. Quantum states in the sense of density metric. Okay? So for example, if I expand, I can expand. So it's rho t minus I dht. But in the case of Brownian motion, you have to remember that dw is of order square root of t. Since my dh, I don't know what's happening here. So dh, it's also at order square root of t because of dw. So I have to go to second order. Minus 1/2 dht rho t plus O of dt to the 3/2. Okay, that I put that on the other side, and I got d rho t. And that's a stochastic equation. And then I apply to all the rule of stochastic equations that you want to apply. Okay? But you see, there is two terms. It's a bit bizarre because it's a unitary evolution. So you will say, there is only like the Schrödinger equation, but you have to keep the second term in order to have the unitary evolution. If you had only this term, you will not have the unitary evolution. Because if the noise is a Brownian one. If it's not a Brownian, that will be different. But at least you have to expand to order dt. Okay, any question on that? So I will not solve it, just to.
Why do we have to expand to second order?
Because dht is typically of order dt because of dw. The square root of dt. Actually, what is hidden in what I'm saying is Ito calculus, but I don't want to explain. But
the first term then is of order square root of dt,
yeah.
which is quite.
No? Yesterday you didn't complain, yeah, yesterday. You should have. Yesterday I wrote dxt, I wrote two equations, is equal to a of xt plus xi of t, okay, first. But actually xi of t square is infinite. So I don't know what the meaning of that, so you didn't complain. And then I wrote dxt is a of xt dt plus dbt. Then I don't have any infinite things, but dbt square is dt, which, so that's a meaningful equality. This one is not a meaningful equality. So this term is of the square root of dt. Nobody complained. I didn't complain, I said. Huh? Yeah, but xt, so xt square, that's delta of 0. You are used to it.
Kind of things is
Yeah, so if you want, you can write E. You want to, then I put dot, 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 dot. So it's true that in the, I am in purpose I put CDAG DW plus Hermitian conjugate. Okay. So in physics you will see CDAG C times psi, huh? Because psi is DW, where is complex conjugate. So that's what I call D dot. So if you want, I don't put the dot. Okay. Yeah, because it was DH. Well, I don't put the dot, but I put the dot here with this H. But then you have psi. Okay. Then you have to give a meaning of psi, which is infinite, actually. Now that's Ito calculus. So I am hiding Ito calculus when I say you expand to. Because, okay. Yeah? Okay. So that's the first thing. Just do stochastic calculus. If there's a way, no, pass integral representation, you can do whatever you want. Okay? That's one trick. Another one is to discretize in time. So I told you that dW is, so I will. So that was the first, so that was the first one. So it was continuous in time. And the second one was discrete in time. So stochastic equation like this one, like dxt is a of x t dt plus dbt. What it means, it means that x of t plus dt is s of t plus a xt dt plus bt plus dt minus bt. So now take a series of increment, call it that delta t. So I could take that, define that to be delta. So that will be delta. And then this is a variable which I can call xi, not xi, eta. And with the mean is eta is delta. Okay? That's a discretization of the equation. And that's how we solve what it means, actually. So now if I take a series of time, I can say that I have series of time, let me, Tn is n delta. So that will become Tn plus 1, Tn, and that will be the variable at time n. That will be at Tn delta. Okay? Which means that I just iterate my recursive relation, but with parameter in it. And each step from 1 to 2, from 2 to 1, the variables are independent. Xi n now it's delta times delta nm. Okay? That's how you discretize stochastic equation, no? I just do some small time interval. So I can do the same thing here. So it means that if I have in time, so that's time, I will go from t0 equals 0, t1 equal delta, t2 equal 2 delta, and so on. Tn equal, so n delta, tn plus 1, n plus 1 delta. Okay, can do that. And then the evolution between, so when I go from Tn to Tn plus 1, I have a unity, so I have some unitary evolution, let me call it Un, which depend on the parameter eta n plus, so that should be n plus 1 if you are correct, n plus 1, okay? And the n plus 1 is independent of everything. So in the case of QSEP, I should keep QSEP, UN was more or less a good approximation, will be exponential of sum over the site, C dag G plus 1, Cj eta n plus 1, plus blah, 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 blah. Okay? Plus Hermitian conjugate. Or maybe there is a I. So these are operators. The J refers to the site, and that's the random variable. Okay, that's just a discretization. Okay, except that there is random parametering. Now, these operators, they don't commute because they are attached to us. Wait, I don't know what to do with.
I think you lost the connection.
But okay. Yeah, no. Well. So another way to write it is to, so these operators C, so here I have J, J plus 1, J minus 1, G plus 2, G minus 2. So these operators C, they are attached to the edge, this edge. And this operator C dag on this edge commute with that one, but not with that one. So what I can do is to group this pair of this edge together and group the edge which are complementary together, okay? So up to small errors, if delta is small, this will be the same thing as Wn, Vn, where the two operators commute, but Vn is the same thing, is exponential over the G odd. So it corresponds to that site of C dag C. So this depends on J too. G plus G eta G plus Hermitian conjugate. And V, so that's, and Vn is exponential of, so Vn is equal to exponential to I, sum of G even, C dag J plus 1, Cj eta G. And this corresponds to this edge, okay? And then, of course, this is not exactly inequality, is up to errors which go to 0 as delta goes to 0, okay? Commuted.
Quick question about the notation. Here, eta is once again a complex noise, right?
Yeah. So I have just discretized. Instead of writing dw, I wrote eta. And then what I say is that the exponential of my Hamiltonian with random variable, and I wrote it as a product of two objects which commute because it's more convenient. Okay. So this one do not commute, but every term in the exponential commute. So this one I can write as a product of operators. So now I have a representation of this one. So here is J. Now, poof. So I have first my evolution for the W, which act here. I act with the W. And then I have the action with the V. So that should be yellow. And this comes with parameter eta, they are random. And then I act again with the W, but with another set of operators. And then with the V. And then again with the W. And I can keep going for hours. Okay? And so each of these drawings correspond to an interaction. So these ones are typically exponential of I C dag C times eta plus Hermitian conjugate, where the C and C dag are on the edge. Eta is my random variable. I have one eta per, for this, you can call it some gate, for this gate. And they are all independent, and they, okay? So that's what is called a random quantum circuit. And that's what Lorenzo will discuss next time. So output, and then I answer the question. Discretization of these stochastic processes is the same thing, more or less, as a random quantum circuit.
mean by the t exponential reduced to this?
That?
The t exponential, because usually when you solve such
Yeah.
you get a t exponential.
What is a t exponential is the product of that when you iterate, no? That's what you mean. So t exponential is just to iterate the equation. T exponential is just defined by differential equation, so it's just a iteration of how to write it, where to write it. So when you said ut is t of exponential of integral of dht, that's ds, that's what you want to write. That's the same thing as saying that ut plus dt is equal to, how should I write it? E dh of t plus dt ut. dt. And you iterate. So what I am just doing is that I discretize your t exponential. So the purpose of all these discussions was to introduce that this is a random quantum circuit that Lorenzo will discuss. If the random, depending on how is the randomness, how are the gate, but they define some kind of quantum stochastic processes actually. Okay. Well, we can do a break, and then after the break, I will describe more the tools to study open system, which come from that. Yeah. So, any question before the break? Yeah.
I didn't understand why, in order to preserve unitarity, we need to have a term proportional to dt.
Because of the fact that so in this equation, it's clear that you preserve unitarity. So it's because the Brownian motion is very irregular, and the regularity is reflected in the fact that the order of dh of the Brownian motion is square root of dt. So I don't like this way of writing. So if you accept that, it's clear that you have to expand. Okay.
I don't see the connection between having a term proportional to dt and preserving unitarity.
So the connection is that way, but otherwise I can do in the reverse. So do you understand the connection from that direction here? What you don't understand is from here. Is it? Which connection you don't understand? So if you understand that you're going from that from here, you see that because this was unitary, if you didn't include this term, you will have only the variation of rho at order square root of dt. For example, okay? So if you wanted to have at order dt.
I guess I don't understand if you only have the square root of dt term, why would the equation be non-unitary?
I am trying to, because I have to, if I want to answer, I will have to do some stochastic calculus. I'm afraid to. If you have only the, so for example, if I was waiting, how to explain to you. So something, but I wanted to do it later. So if I take the mean, so there is two ways. So let's look at the mean. So this has some evolution, but I wanted to do it later. So if I do the mean, I just have to, if I want to compute dt of that, or dt of that, I have to look at the mean, so times dt. Okay, and then I plug this formula here. Okay, now so there is two terms. There is one term which is E of the commutator, and there is a second term. And why I have difficulty to explain is that I am implicitly assuming that I do Ito calculus, which I didn't explain to you. And you know there is various ways of doing stochastic calculus, Ratanovich, Ito, blah, blah. And the presence of this term depends on which convention you use for the calculus. So now if I want to compute that, I have two variables. So the mean to compute that will be the mean minus I of the product of two variables. Okay? These two variables, so they depend on the disorder. So the mean, they can be correlated or not. Okay? And the fact that they are correlated or not depend on the convention you take for the stochastic calculus. On the convention I take everywhere, you see, when I say that this variable independent is a random variable is the next step, which is the random variable which describes the evolution from the step n to the step n plus 1, is independent of all the previous one, which means that this variable is independent of that one. That's Ito convention, without saying it. So this means that in the way I write, I use Ito without telling you, and this variable is independent of that one. Okay? Because I am sampling the Brownian motion after time t, the increment from t to t plus dt. So it's independent of that. And because it's independent, then this expectation is the product of the expectation value. So it's 0 because the expectation value of dh is 0. So if you only add the first term, so if you, that will be 0, so the evolution, it means the evolution of the state will be 0, which is a bit absurd because you are in contact with, you are evolving in contact with the environment. It will not be stay constant, the state in mean. Okay? But hidden in this computation is the fact that I am always sampling the processes using Eton convention, means that I run the process up to time t, and then I use the increment to go to next time. And the increments are independent of what happened before. Yeah, does it answer the? Okay, we stop. Ah.
How would you add any measurement to this? Because
Yeah, I was
doing things that are not measuring the quantum system.
Yeah, so that's what I was. If I have time, I'll describe afterwards. That's what is called quantum trajectories.
Can I ask, like, I don't see how are you able to split this even and odd terms into two separate pieces, like this unitary evolution operator even. How does it work that you can, like, I understand that they commute like all the not neighboring lattice sides.
So we have U is exponential E, let me call it Hn, okay? All this operator. Yeah? And Hn is the sum over the site on EHn odd, where just sum over the odd site plus I Hn even. Okay? What I say is that this is equal to up to, since I didn't tell you what are the errors, that's okay. Huh? Do you agree? And then what are the errors? You know there is this Baker-Accuser formula, whatever. So that will be, these things will be exponential of the commutators, maybe minus of odd times even, and even, n plus all the multiple commutators. So this one, they do not commute. But when you do commute, you will have the product of the eta. So these one are of order, so each of the term, so this one is of order square root of delta. By my convention, eta square is delta, so square root of delta. This one is of order square root of delta. So this one is of order delta. So it's small compare when delta is small. Of course you do a mistake, but we are discretizing, so we are aiming at taking the limit when delta goes to 0. Well, but sometimes maybe bad things can happen. But
So in itself, omega and v do not, omega n and vn do not commute, but only up order of delta.
yeah, this one they do not commute. Yeah.
Because you have Cj side in
Yeah. But then each term, why I'm doing this decomposition is because now if I look individually at that one, the term which are here, they do commute. Huh? So I can write it as a product of operator acting on each of the links. That's what I implicitly draw here. So here, it's a product of these operators. You can do them in any order you want. Here, it's a product of these operators. Of course, you can, okay. If I would have started with the yellow gates and then the white one, it will not be exactly the same thing, but delta goes to 0, I cross finger, and I hope it works.
So I have a, but if this will be worried by the fact that you have to expand after the second group in this class.
No, because I keep unitarity, I think so. No. I never use the discrete one. I always use the continuous one. But no, because second order is, you see, it's when the delta t do the evolution. So that's still, I don't think you. Yeah, now what you have to wonder, I think that here you make an error of delta. And then you want to iterate during long period of time, of order 1 over delta, if you want a finite time. And then you have to check if the error do not accumulate. And that's super difficult to control. So I say cross finger.
Just a small announcement. Okay, the detector is gathering closer for a photo.
Okay, so I told you that here we had a system, and then we have noise variable around it. Noise. And at least in what I was describing, this was a closed system. And as a consequence, so rho, which is a state of system, not of the noise, evolve randomly. So rho t of omega okay, that's what I just said. But I can view the noise as another system. And then when I do the expectation value over the noise, it's like tracing out the degrees of freedom of the noise, okay? So averaging over the noise. So in a way, the system is not by itself an isolated system. It's interact with the degrees of freedom that I have represented by the noise, okay? So it means that the system by itself is open because it interacts with the system. Okay, so system plus noise. That in a way it's closed. And if there were a reservoir, it will not be closed, but in that case, it, with no reservoir. But system by itself, it's open because it interacts with the noise, because of freedom interact. Okay? So, if I don't care about the noise, I will trace out the noise, which is the same thing as doing expectation value. Okay? So, that's the same thing as expectation value. And then the evolution of the reduced density matrix when I reduce to the noise of the average one. Okay, so of the reduced or the mean system density matrix is not unitary. So what it is, I define rho is the expectation value of rho of omega, okay? Which again is the same thing as a trace over the noise of rho t of omega, okay? So what is the evolution? I compute the mean. So imagine that all the events happen with a probability, I don't know, you give a name, P of omega. If P of omega is the probability of occurrence of omega, omega is an event, which means a realization of the noise, then rho bar, that's rho bar. Huh? Rho bar of t, that will be the sum over omega, p of omega, ut of omega, rho, ut dag of omega. Okay? It's not unitary. And that's an example of quantum channel. So quantum channels are actually all possible transformation on states of system, which are compatible with the facts preserved. So that's rho, but rho initially was the rho bar, which preserves the positivity of the matrices. Actually, a bit more. Maybe I will explain. Preserves the trace of the matrices. For example, so it's clear that rho bar is positive because each of the term is positive. I do the sum. So rho bar is positive. It's clear. If initial rho was positive. And if I compute the trace of rho bar, so it's clear that it will be 1, because for each realization, the trace of rho was 1, so in mean it will be 1. But I can check it here, so it's 1 by definition. But if I want to compute, it's P of omega, trace of that, which is U, rho. Then using a unitarity, that will be I can put the U here. The U are unitary, I can forget then. This is the same thing, so P of omega is 1. So that's an example, okay? Now, so what, why I did this computation is to show that also for each realization, the evolution is unitary. In mean, they are not.
About this, what do you call omega as a realization?
Omega is a, yeah.
The full history from like 0 to times t of the disorder, or is it?
Yeah. But, for example, even in the example that you had in mind before, for example, for Anderson localization, this is not done usually, but you could do it. So you have an Hamiltonian with quench frozen random parameters. You evolve the system. Then omega will just be the choice of these random parameters, an event. Every time you have randomness, you have events. So your parameter take value in some probability space, and the point in this probability space, you call them event. Okay, that's what I call omega. It's a standard name, just to. Okay? Any question? So that's an example of open system of a CP map, a dynamic for an open system. So again, dynamic for open system because it's open. It's not unitary. Okay, but it preserves the notion of probability, positivity, sum to 1 of the probability. So I will give another example, which then will be useful for if we do monitoring. So that's one example. But, okay, so as you can see, this example is generic, but you can apply it to the stochastic dynamic I was mentioning. Then omega in that case is the history of the noisy variable that you have chosen to define the stochastic dynamics. You can do the same thing for the moments. So if you look at rho, second moment, rho tensor rho, then there will be a big unitary evolution in the H tensor H, two replica of the system. And then you will take the average, and then the average will not be anymore a unitary dynamic in H tensor H. It will be another CP map, but in a replicated Hilbert space. So we can do another, I will do another example. And this example will be useful, as I said, if we discuss quantum trajectories, if we have time, probably not. So imagine that we have a system, any system, many body, few body, and so on. And then we probe the system with another one. So we use probes that we prepare, so there is a probe. So we prepare in a state phi, so that's preparation. And we send this probe through the system, so there is some interaction during some time. And then potentially we observe or not the probe. So it means that after there is the interaction, we can do two things. Either there is two options. Either we observe, measure. So either measurement or observation. Of the probe, not the system. Or we don't care. It means that we are going to not observe the system, okay? So we'll trace out the probe. And the second one, not to care about the probe, it means that even though you had measured the probe, you will not register the output measurement. That will be the same thing. Okay. So we can do that. Actually, this was, and then to discuss quantum trajectories, and we are going to iterate later on. And then possible iteration. And that was a series of experiments which have been done in many, many places. Actually, every time you study small qubits, that's what you do, but the probe is you change the way you probe the system. But this type of experiments were done by the group, some group at ENS, by Haroche. So it's called the photon box of Haroche. Haroche photon box. And he got the Nobel Prize 10 years ago for that, for this kind of experiment. So the system was, that was just a cavity, electromagnetic cavity of very high quality, selecting one mode. And the probes were Rydberg atom. But only two orbitals matter, so they behave like spin half. Or qubit states. And that was used to, so this series of Rydberg atoms are used to test the system. And you see that this system is open because it interacts. So I will describe that just to first, if I don't care, and then if we measure, and that will lead to quantum trajectory and what happened to how the measurement backact on the system, if I have time. So we have the system. So what we have the probe. So we say initially. So initially, instead we have the system in state rho. So then I can say that if it's a pure state, it's okay. So that's the initial state of the system formed by the probe and what I call the system. Okay, and altogether it's closed in a way as a system plus noise was closed. And then there is interaction during a time. So let's say take the probe to be spin half. So I take this one to be spin half. So with a basis plus minus. Maybe I will do the quantum trajectory right away. So then there is some interaction during a small period of time. So interaction during delta tau with some operator. I will call them U. So U, we always nothing to do nothing to do with that one. So maybe another name. Okay, so some operator U, or maybe a script U. That's the interaction between the probe and the system. So it acts on the tensor product during the period where the probe goes through the system. Okay? And then after, so that's initially, so there is some interaction. So then the state of the system will be U, phi times phi, tensor rho, times U dag. Okay? And then now you measure, let's do, so we do the first option. So now we measure observable phi. So that's what I will do. So let's say that we measure sigma z. Sigma z, okay? So the output, if we measure the probe, the output can be plus or minus, okay? Depending on the states, if we get plus, the probe will be projected probe is projected on plus or minus. And, okay. So, what will be, imagine that you get plus, so after, if measurement, if is plus, so the states, so we have to project that on the states. So it means that after the measurement, the probe will be the state of the system probe times what I call system will be factorized. The probe will be in the state plus, and the system it will be in a new state, not rho. It has been changed. I will call it plus because it's conditioned on having plus. And that's obtained by projecting, according to Born rules, projecting on plus. So that will be, this state will be plus u phi rho phi u dag plus normalize by some normalize, and I will call it pi plus the normalization. Okay? I just use Born rules. That's just Born rules. On P plus is what? Is the trace of the object here, so it's the trace over the system of plus u phi rho phi u. Okay? So that's what, by Born rules what happened after the projection. And this pi plus is actually the probability to get plus as an output, given that the state was here and given that we were measuring sigma z. So that's that with proba. Okay? Do you follow that? So if I obtain minus as an output, I will be projecting on minus and a minus everywhere. So what you see is that you start to so system interact, you extract a bit of information from the probe, and you have modified a bit the system, a small back action of the system. Okay? And then I will show that, I will write it a bit in a different way, and then we'll discuss it a bit more. So this means that after, so let another way to write it. Let k plus phi plus minus. So then, but I will write something here. Then rho plus minus is just k plus minus rho k plus minus dag over p plus minus with proba p plus minus is trace. The trace is over the Hilbert space of the system. K plus minus rho k plus minus dag. Okay? I'm just copying Bond rule formula. And what I have, if I compute K plus my formula, DAG, K plus K minus DAG K minus. So it's clear that this is so this appartiens aux endomorphisms of the Hilbert space of the system, because U was acting on the tensor product of the Hilbert space probe times system. I take sandwich with respect state on the probe Hilbert space, so I get an operator on the system. So if I compute that, what do I have? I have phi U plus U DAG phi plus phi U minus U minus U DAG phi. Okay? Just copy. No, that's the let's type here. Okay? Now you see that this piece here, this piece is here, this piece is here, so I can write here that as, so I factorize, so I can write that as plus minus, okay? Which is an identity on the Hilbert space, so that I can forget. Now U is unitary, so I get, so this means that as a second step, U DAG cancel, and then phi is normalized, so this is 1. Okay? So that what we have found here is a general structure of quantum trajectory. So what we have a series of operators. So if I forget, so that's the output, and they satisfy some relation, these operators, and then we have a transformation. So in general, what we have, if it was not a alpha probe, we have K alpha, let's say M, a family, so M, K1, K big M, which I will call as Km, operators on H system, indexed by some M that you will call output measurements. They satisfy sum over M Km DAG Km equal 1. Okay? And then, if output measurement is M, then the state of the system is updated according to, is updated as rho to rho which depends on M is Km rho Km DAG over pi M with proba pi M is a trace over Km rho Km DAG. So that's a generalization of Born measurement. Just if you want, what you have done is that you have some apparatus. So if you implement Bond rules, you will measure the system and project the states. Here we have moved by one step what is called the Feynman cut, where you put the limit between classical apparatus and quantum one. So our apparatus is a probe. We view it as a quantum system, and the classical cut is put after the probe, so that we treat the probe as a quantum system, and so we measure it with a classical system. That's what we did. So that's, if you will see in the literature, this set of operators, or this set of measurements, they are called POVM for projective maybe, operator value measurement. So it's something like that, that's POVM. And that's called, there is the various name, indirect measurement. So it's called POVM measurement. Indirect measurement. Weak measurement. That's different name used. And of course, you can iterate the process. So you can either, I told you that the output can be M. And now if I iterate, I will have series of M1, M K, like K, and so on. And that will be my new M, if you want. And then you will apply the same formula. So you can either iterate or not. So, okay? And if you iterate, this means that every time you will do a measurement, you will update the states, and you will update it in a random way. So it will define for you a stochastic process. And this iteration updating is what is called quantum trajectories. So under iteration, simply updating of the states in a stochastic way. And that this series of updating is what is called quantum trajectories. So the trajectories is trajectory, so it's quantum, because it's a trajectory is a stochastic evolution in the space of state of the system, state in the sense of density matrix. So here, it's stochastic because the evolution is random. It happens with some probability depending on the output. So you may think that if it's random, it's noisy, but actually all the information is in the noise in that case. All information is the noise, because the noise is output measurement. Now we can look at what happened in mean if we trace out, and then I will make contact with that. So in mean, so if we trace out the probe, it means that we have to look at the mean states after each iteration. So we say that if M was the output, rho goes to rho M, which is Km rho Km dag over pi M with proba pi M. So the mean, so rho bar, that will be the sum over all possibilities, output measurement, of the updating of rho M with the proba of having M. Okay, that's the definition of the mean. Okay? So what is the proba for output? By definition, it's pi M. So that's sum over M, rho M, pi M. What is rho M is this formula. So it's the sum over M, Km rho Km dag over pi m times pi m. This simplify. And so we find that in mean, rho equal to rho bar, which is sum over m, km rho km dag, which is, I give a name, I call it phi of rho. And that's the definition of a quantum channel in general. That's the definition of quantum channel. That's a terminology in physics. In math, it's called complete CP map for completely positive map. The Kn, which are elements of the P of M, in that context are called Krauss operator. And what you can see is that this formula, so the condition star guarantees that trace of phi of rho is 1. Because when I take the trace, cyclicity of the trace is here, and then you get 1. Of course, rho is positive, this is positive, so it's a term of positive, rho is positive. And complete positivity is a bit more. It means that it has to remain, even if there is another system nearby, but on which you don't act, and you require that after transformation of acting on the system without touching the nearby environment, the state of the system remain positive. This is stronger conditions that preserving the positivity. It's what's called complete positivity. So there is maps which are positive but not completely positive. So and you see that the example I gave here. So the K are arbitrary. It just satisfies this condition. Here, in that case, this corresponds to the cross decomposition. If I do a slight modification, I don't modify the formula, but there is a P omega. I will put a square root here, and I will put back the square root here of P. And now I call that K of omega. And that's K dag of omega. And then you see that this formula is simply sum over omega, K omega, rho K omega dag. So it's a particular case of CP map. Particular case because the K are constructed in terms of unitary operators. In general, they are not, for example, in the example I gave. Yeah. Yeah, that's what I did when I said trace out. And if you trace out, that's what so as I said, tracing out the probe or not registering the probe is the same thing. It's why you look, when you compute the mean, it's what you do. Huh? You do something on the system because the probe has interact with the system, and then you trace out the probe, so it has modified a bit the system. Okay, but you view the probe as noise, so you forget about it. Whereas when you do, so that's what happens when you don't want to look at the probe. Either you do measurement but don't look at your notebook where you put the measurement output, or you don't do any measurement. So you trace out, and that's what will be the transformation. And but you may also look at the probe, measure, and that's what you do when you extract information from the system. And because you extract information, the series of output measurement, you modify the system a bit and in a random way. Okay? Exactly. Or you will have measure, but you will have keep your notebook closed and not look at it. Stop. So, yeah. So what I didn't say, so now you can look at map for open system which depend continuously on time. Then there will be, if it's a semi-group, there will be an operator which describes the evolution which generates the evolution by infinite amount of time. That will not be an Hamiltonian, that will be another operator which has a specific form, and that's called a Lindblad operator. And then, well, and then there was we can discuss string hours. I stop there. Questions? No, we don't have time.